don't know if you've noticed this already, but I've made a bit of an observation here that I want to kind of explore with you here. I've reproduced at the top here the electric circuit that we studied a while ago. And then I've also put down below the mini tube with this random tourist journeying around on it that we just solved for. At the top, I've put all of the data that we found, the voltages at the nodes. In particular, what I did there, remember, was I put node 1 at unit voltage and I grounded node 2, and then I solved for the voltages at nodes 3 and 4. And then in the randomly journeying tourist problem on the mini tube, I found these probabilities that if she starts at nodes 3 and 4, she gets to Bond Street, node 1 before Green Park. And in the electric problem, we also solved for what I called the effective conductance, which you can just about see there. It's F hat, or CF, I called it, which is 8/5 we found. And although we didn't find this analytically, we did do some numerical simulations, and we found that something called the escape probability, which I'm denoting here by P-ESC for escape probability, we found it to be about 0.8, didn't we? Which is about 4/5. Well, it's actually 4/5. What I mean is we didn't find that number analytically. We did, however, find P3 and P4 to be 1/5 and 2/5. We found that analytically using basic probability theory. Okay, now you see, the first thing I notice about this is that, first of all, the graphs are identical. These are not the same problems. One's a mini tube, a subway, and the other one's electric circuits. They're completely different things, but mathematically they're given by exactly the same graph. They've got 4 nodes and 5 edges, and in fact, the topology is exactly the same in both. And in fact, I've even gone so far, look, to label all of the edges with the same numbers. So even the numbers are in correspondence. So I've noticed that, and of course, the other thing you will have noticed, look, because I've put the numbers that we found in both problems on there, you'll notice that the potentials we found in the electric circuit problem seem to be exactly the same as the probabilities that we found in the random journey problem for all values of I, 1, 2, 3, and 4. You see, P1 is 1, X1 is 1, P2 is 0, X2 is 0, P3 is 5th, so is X3. So that's kind of remarkable, isn't it? And there's a final observation that I'd just like to make. Look, we didn't find P analytically that P escape, the escape probability, was 4/5. We didn't find that yet, but we did find it numerically. And I don't know about you, but it seems to me quite interesting that the escape probability is precisely 1/2 of 8/5, 4/5. 0.8 is 4/5. Now, I don't know whether that's a serious observation. I don't know what the ramifications of that are yet, but let me just make a note of it. This is what you do if you do research. You make observations, and they could be accidents. But if they're not, that could be something significant. So, interesting. Why should a bunch of voltages and an electric circuit, which we solve for using Ohm's law and Kirchhoff current law, be the same as the probabilities that we just found using basic probability theory for a random walker on a tube, a random tourist journeying around? Don't know. Okay, well, let's focus on this a little bit more to see if we can understand this remarkable observation. Is it just coincidence, or will it happen in other situations? Well, let's just look at the mini tube problem. If you remember, on the last lecture, when I showed you theoretically how to get 2/5 and 1/5, I wrote down the fact that the probability P3, which was probability of reaching node 1 before node 2, starting from 3, was 1/2 using the basic law of probabilities times P2 plus 1/2 times P4. And then I also noticed that P4 was 1/3 of P1 plus 1/3 of P2 plus 1/3 of P3. Okay, that was using the basic law of probability. You remember that? Let me stare at those a little bit more. One thing I've noticed is that there's another way to think about these equations. Notice, look, that this is like the right-hand side is the average of the probabilities at the adjacent nodes. When I say adjacent nodes, I mean all of the nodes that are connected by an edge to that particular node. So for example, P3, 3 is connected to nodes 2 and 4, and look, P3 is a half of P2 plus P4. And then P4 is connected to 3 nodes, 1, 2, and 3, and P4 is a third of P1 plus P2 plus P3. So in both cases, I'm seeing that the probabilities at each node seem to obey some kind of averaging condition, that the probability at each node is the average of the probabilities at the adjacent nodes. Okay. All right, and remember, earlier on, I added P1 is equal to 1 and P2 is equal to 0, and then I solved those for P3 and P4. Let's think about the circuit problem, though. To solve that, I solved a completely different set of equations that I got. Do you remember? I basically solved the divergence of the currents of the nodes is A transpose all the conductances for this problem. Remember, for this conductance problem was this circuit problem was 1, so it actually just reduced to this. Okay, and what's the connection there? Because it looks like the solution for X in this circuit problem is the same as the solution for P if I were to put P into a vector like this. Okay, it looks like X is equal to P. Well, I don't know if you recall this, but remember, this was the Laplacian matrix, and I showed you that it has the following decomposition in terms of degree matrix and what I call an adjacency matrix. In fact, I remember telling you this because it's helpful to think about this decomposition of the K, it's the Laplacian, because it's a simple way to work out what K is. Okay? And do you remember what D and W were defined to be? Well, let's look at row I of this equation. And let's assume Kirchhoff current law holds at node I. That means the left-hand side, which is Fi, the ith component of F, is 0 because Kirchhoff current law holds there. And then on the right-hand side, I'm going to get, well, if you just think about this, the diagonal element of D is the only diagonal element, and that's the degree of node I times xi. Okay? And then the only other elements you're going to get in that row is the minus the sum over the adjacent nodes of xj. Okay? Let me just... Okay, so what I've just shown you then is that 0 is equal to the degree of node I times xi minus the sum of j belonging to adjacent nodes of the potentials there. But isn't that exactly the same statement as that? Okay? Because I can just rearrange this, can't I? To say that xi is 1 over the degree of node I times the sum over j adjacent of the xi's. Okay, and of course the degree of node I is defined to be the number of edges attached to node I. So this is precisely a statement that the potentials in the circuit problem, the voltages they were, is the average of the voltages at all of the adjacent nodes, by which I mean those attached to node I by an edge. Okay, so I work out the number of edges, that's the degree I, and I use that to divide the total of the potentials from the other adjacent nodes. Okay, so solving Ohm's law and Kirchhoff's current law looks like I'm solving the same equations as I got from the basic law of probability. And this is a very exciting observation because it allows us to, if you like, transfer technology between the two mathematical areas, because we didn't think these had a connection, but it turns out that mathematically these two completely different problems, one of random journeys on a tube and electric currents flowing in a circuit, turn out to have intimate mathematical connections that we will exploit.